And we are back, and we are going to continue with the talk by Stratos about the periodic table of data structures.
Hi, everyone. Thanks for tuning for this talk. I'm Stratos, and I'm going to tell you today about our project that we call Data Calculator and how we use that to build systems that are really performant. So the essence of this talk is about data structures and how we make it possible to reason about the design space of data structures. And then we use that technology to for more practical problems, which is building fine-tuned key-value storage engines. And so I'm going to tell you a little bit of both in this talk and how we think there's a future for really making it very easy to deploy systems that are really tailored to the particular context every time. So starting with data structures, so the main function of data structures is to store data, and we can think of them as the data layer and the indexing layer that helps us navigate data structures. So we all know about that from kind of the basics of computer science. The one subtle thing I want to get across here is that when we think about algorithms and when we think about systems, data structures is really the very first thing that that we have to do. Well, when it comes to data-driven problems. So, for example, when let's say we have a simple array, okay, with just integers, and if there's no order in the data, and we want to find a particular key, let's say, then there's no way around just, let's say, worst case is having to search everything. Okay. While if we say, okay, let's do better, let's think of a better algorithm, then the algorithm really starts by asking the question, how should I organize my data? Okay, and so if we say, for example, okay, let's flip it around and fully sort the data, then we can do some kind of binary search. Okay, and then it can be faster. So really the point here is that when it comes to data-driven problems, thinking about data structures is the first fundamental thing that we do when we design something. And then when it comes to systems, so more complex entities that we build on top of data structures and algorithms, really the best definition of a data system, from my point of view, is that it is a collection of data structures and algorithms that they all work together to achieve some higher level goal. Okay, so effectively some higher level, more complex behavior than what a single data structure would do. And we'll use that definition. We'll come back to that quite often in the talk. Now, why data structures are critical? So actually the point is that not only they are critical, but they become even more critical as time goes by. And the reason for that, or one of the big reasons for that, is that the way hardware works is that hardware that we use for computation, such as GPUs and CPUs, they're actually becoming relatively faster compared to our memories and our disks. Okay, and so of course, data structures, since they define performance, they define how we move data from memory up to the CPU or GPU, and so they are the fundamental component of a system that defines performance. And it's not only that we have a single layer of storage. Typically, we call a memory hierarchy. And that complicates things even more because that's a hierarchy of different kinds of storage hardware that has its own different performance properties. And so having to understand this whole thing creates even more complication. And for example, Jim Gray used to say that if an algorithm or a system is looking for some piece of data that is in the CPU registers, then it's as if a human being is looking for something in this room, while if the data is on disk, it is the equivalent of a human being looking for something that is not even on this planet. Okay, and that kind of gives us a very nice mental image for how we should be treating data structures as a first-class citizen. Now, okay, they are important in terms of performance, but why this is an intellectually interesting and challenging problem? So the thing is that there is no perfect data structure. Okay, so anything that we do, it's effectively a trade-off. And the main trade-offs to consider are the read, update, and memory amplification. One way to think about amplification in simple terms is that if, for example, for read amplification, if I'm looking for a particular, let's say, key value pair, then every single item that I have to touch as part of this process, on top of that particular key value pair that I'm looking for, that is an overhead. Okay, that is my amplification. And I might have amplification for many different reasons that go all the way from data structure design, algorithm design, and the hardware properties. And so anything that we do, any particular design, it is really a trade-off on that space. And any particular class of data structures is not able to cover all of that space, but rather a small area in that trade-off space. And of course, it's not only about read, update, and memory amplification. In fact, the problem is way more complex because each one of those trade-offs, they actually break down into furthermore trade-offs. So for example, it's very different if you're doing a point query versus a range query in a system. And it's very different if you're doing an update or an insert or a delete. So each one of those access patterns would require different kinds of algorithms and data organizations for optimal performance. And so the trade-off space is actually way bigger. And finally, when it comes to systems that use multiple different data structures, we not only do we have to tune the different data structures and design them in the best possible way, but the additional problem is that now we also have to worry about how those data structures interact. How do they play together to achieve a more complex behavior? And so, for example, if we look at in particular into key value storage, and then within that into LSM3 based designs, you would have the different levels of the LSM3. Okay, and you would have a buffer in memory. You would have also in memory filters that help us avoid access to disk. You have fence pointers that help us go into particular pages on disk. You would have caching that again can help us, find the data right there as opposed to going down to disk. And of course, the different levels on disk of the LSM3. They can be different data structures themselves. And so the key here is that not only each one of those data structures is critical to optimize by itself, but understanding how they work together is a very complex problem on top of the single data structure problem. Okay, so the essence of that is that there is no single data structure, and so there's also no single perfect storage engine. Okay, and why this is a problem? So key value storage engines, they're really everywhere. Okay, so we obviously use them as kind of NoSQL systems, and as such, they actually appear in so many different applications. We also use them in SQL systems. So first of all, you can achieve SQL performance, SQL behavior on top of a NoSQL system, but also you can embed key value storage engines as part of SQL systems, such as to achieve catalog behavior or indexing behavior, and so on and so forth. Similarly, in data science, machine learning pipelines, you can use key value storage systems to store features or other kinds of data in time series systems, in graph systems, and in many more applications. And we keep building new kinds of applications, as you all know. And so there are critical problems. How do you go about choosing a storage engine? How do you go about giving a storage engine? How do you go about tuning that storage engine? And if none is good, no storage engine is good. Do you, for especially for big organizations, do you design a new one? And how do you do that? Every time that something changes your application or in system, how do you deal with regression costs and so on and so forth in such a dynamic environment? And then the thing is that there's multiple different kinds of costs that are very important today beyond the pure performance of the system. So for example, how much are we spending on the cloud? How much developer time are we spending in building applications, in tuning the system, and so on and so forth? Okay, so ideally we'd like to make it so that we have systems that they make it easy for us across all those factors. And so if we look at what is happening out there in the world today, we can say that we broadly have two kinds of key value storage engines, LSM3-based key value storage engines and B-tree-based key value storage engines. And we think of them as two discrete kind of areas. Okay, and we go in and we build different kinds of systems that are based on these fundamentally different data structures. And so The point, again, going back to my previous point, the point is that with diverse workloads that are slightly different every time, ideally what we would like to do is not have a fixed system that has a fixed behavior, but rather be able to tune the system for the particular context, for the particular budget and the particular workload of a customer. Okay, so that leads us to the realization that, hey, it would be perfect if we could automatically design data structures, right? Then all our problems would go away. We would have a particular workload, boom, we would get the best data structure design with minimal human effort, and also that being the best design possible. So what is interesting is that in computer science, everything was about automation since the beginning. So ideas about automation have been appearing throughout the last 50 or 60 years. And so when it comes to data structures in particular, I really love how Rob Tarzan put this in late 1970s when he said that we should be working towards a calculus of data structures. So he had this vision paper where he laid out the 5 big problems of computer science at the time, and kind of all of them are actually open problems today as well. So what we're doing in our lab at Harvard is that we are working on exactly that problem, and then on top of that, we're also working on a calculus for data systems. Okay, and today I'm going to give you a little bit of a few hints for both of those things. So the first one is when it comes to calculus for data structures, our system that we call the data calculator that helps you automatically design data structures for a particular context. And then the second part is what we call self-designing key value stores that use the previous technology to actually build complete storage engines automatically. So when it comes to the science behind this, it is really, the whole thing is based on 2 fundamental questions. That we narrowed down the problem into these 2 questions, and that helped us kind of go towards a solution. And so the first question is, can we somehow get a handle on how many data structures is possible to ever design, and which are those data structures? I understand that this question might sound a little bit weird at the moment, but you'll see where this is going in a while. So this is what we call the design space. What is the possible design space of all possible data structures we may ever design? And I'm using the word all here with a little bit of freedom. Then the second question is, given the design space, can we actually compute the performance of the different designs in that design space? And can we do that without actually coding anything? Okay. And then the claim is that if we have those 2 components, then we can really think about automatic data structure design and eventually self-designing data systems. And I'll try to lay out a little bit of that work over the next 20 minutes or so. So why this is possible? So if we think, let's start with data structures, okay? And we will discuss storage engines in a while. So if we think about data structures only, then we can think of a particular data structure design as a set of design decisions that we made when we came up with that design, okay? And then every time we have a new design, it basically falls in one of 2 buckets. It is either a collection of existing design decisions, maybe we put them in a different way together and so on and so forth, or it might contain at least one fundamentally new design concept that nobody thought before, okay? And the main thing that we observe is that by now, basically more or less everything that we do, both in research and in industry, is that effectively we're putting together design concepts that have been invented in the past, and we're putting them together, and we're by that we're creating new designs. And so what we want to do in our research is to figure out what are all these possible fundamental design blocks, fundamental design concepts for the design space of data structures, figure out how they can be combined, what are the properties that you get in terms of performance every time you combine a few of those design concepts together to create a final design, and what does this mean for the final design in terms of how it is placed in the possible design space, in the possible design trade-off space. Okay, and the point is that if we know that now, given a problem, given a work, given a hardware, given a cloud budget, we can actually build algorithms that go and choose the best design for the problem at hand. Okay, now, okay, so that sounds like a, I hope you find this as a nice vision. Now, how do you actually do that in practice? Okay, so there's a lot of trial and error going on. Let's start with a basic thing, which is, how do we figure out what are all these basic components out of which we're going to synthesize data structures? So there's a lot of trial and error here, and basically a first principle component is really a design concept that you cannot break down any further. So, for example, think about a very low level design of a data structure. You can have an option. You have two nodes of data structure, and you draw a pointer. You create a pointer from one node to the other. So that behavior, that design, you either do it or you don't do it. There's no way to break that down any further. So that can be a design concept that you enable as an option in that design space. The other part is that we're separating the algorithmic aspects of the design versus the layout aspects of the design. So we have a separate design space for the layout of the data structure versus the algorithm, how you actually access the data structure. But we do both, and effectively, our process for the last 7 or 8 years that we're doing this work has been about using that design space both to answer, both to map existing designs that we know from the literature, and to answer open questions in the field, which actually helps us to fine-tune that design space or actually answer open questions in the first place. So, for example, let's be more practical. When it comes to LSM trees, what is the size ratio? What is the merge policy? How many filters you're using for the Bloom filters in memory, and so on and so forth? These are fundamental design decisions that are part of the design space. Okay, and so what we're doing is that we are identifying all those design decisions, and then what we're doing is that we are asking the question, what kind of different values may they take, each one of them, and then when you combine the different values and you create different synthesis of that, of an LSM tree in this case, how does it sit in the trade-off space? Okay. Now, let me make this a little bit more practical by showing you an example of some of the work that we're doing. Now, this is a typical LSM tree. I can visualize a typical LSM tree, and what you see is, what you see in the main box is stuff that will be on disk, which is the different levels of the LSM tree typically. What you see outside the box is stuff that will be in memory, so the buffer and the blue filters that you have in memory and the filters that you have in memory, and so on and so forth. And so a very typical decision here that all systems out there have is that you have fixed bits per entry for your blue filters. Okay, so what this means is that every filter for every level is kind of tuned, is actually treated in the same way. But what we realize is that for different kinds of operations, this is not really optimal. So, for example, if you see what is the worst thing that can happen in LSM tree, is that you're looking for data that does not exist in the tree or exists at the very last level. And so you have to go all the way to the last level to figure out if the data is there or not. And so then the performance that you're getting out of the system holistically is not really performance of every single optimized Bloom filter, but holistically across all of them. And so what you have to optimize is for the sum of the false positive rates across all of them, as opposed to each individual one. And then once we understand that, well, the same memory budget is more impactful at smaller levels than at bigger levels, and that's because we have also the fence pointers. Every single I/O every single time that the blue filter says, "Oh, you should not go," you should go into and search that level. What happens is that we're going to do at most one I/O, and so effectively all of those filters are contributing in the same way in the worst case performance when we have to go all the way down. But if we take just even a couple of bits per entry from the last level that has so many items, and move them to the top, now that same number of bits can represent a substantial improvement in terms of false positive rate that is effectively visible across end-to-end performance in the system. And so, long story short, if you can define this as an optimization problem, which can be solved rather quickly, we end up with a different kind of set of bits per element for the LSM tree that gives us a massive improvement in performance compared to existing systems. And so that's what you get in terms of modeling, and that's what you get in terms of performance when you implement this design in RocksDB. So what you see on the x-axis is entries, on the y-axis is response time, and you see that the response time remains quite flat. And this is actually Monkey implemented in LevelDB, so it's the same system with only that difference in Bloom filters and lookup cost. A similar design optimization. So starting with the same optimization here, the next question to ask when you're thinking about primitives is, why should all levels be kind of leveled? So there's two kinds of policies that you can have here. Either you create runs that consecutively hold all the data and they're sorted across, or you have smaller runs that are being accumulated, kind of like a log, and one helps with reads, the other helps with writes. And then systems typically make a single decision that is true across all the levels. Sometimes the top level might be tiered, and everything else might be leveled. So our observation here is that, well, not all levels contribute equally to the different kinds of workloads that you might have here. Okay, so what we realize is that if we actually again define this as an optimization problem and start thinking about every single level, should it be tiered or should it be leveled, and tune that for the particular workload, then what we get is yet another big boost in performance. That again, it can be materialized in optimal performance. And so this is what you see Dostoevsky here is an implementation of that idea on top of Facebook's RocksDB, and this is normalized behavior. So you see that how much better this can be for different kinds of workloads in terms of read and write, mixed read and write performance. Okay, so at some point, this is twice as fast as RocksDB. Now, this is not only that was kind of a dive into LSM trees, but this is not only about LSM trees. What we do is that we do that across different families of data structures. We figure out these design elements, we combine them, we bring them together to a big design space, a big design space of possible design concepts. And what we do is that by giving values to each one of these design concepts, effectively you're designing different kinds of nodes of data structures. And so we have a design space of nodes of data structures, and then by combining multiple different nodes, you actually get full data structures by defining how the nodes interact with each other, and by doing that, we were able to actually formalize a lot the design space of data structures. So we even created what we call the periodic table of data structures, and what you see is actually it's quite empty. So here you see on the left the different classes of design primitives of data structures, and on the horizontal axis you see different classes of families of data structures. And when you see done, it means that there's at least one system or research paper that we know of that supports this kind of combinations, but most of it is actually quite empty, which means it's actually unexplored, or it's not really mapped formally in some way. And we also give you guidance about how you should use it if you want to design a new data structure. Now, I'm going to go a bit more quickly through the rest of the part. Now, once we have the design space, we build what we call this data structure alchemy system. That effectively what it's doing is that it starts with the design primitives that can be synthesized in multiple different ways to create different kinds of data structures. And so then we have what we call the data access primitives. This is the algorithms that we use on top of it. And with those primitives, we synthesize algorithms. And then we learn with machine learning how these primitives behave in different hardware. And then we synthesize the behavior of different kinds of operations through through those learned components. And so then we can build get operations, put operations, delete, bulk load operations, and so on and so forth. And so that gives us both the layout and the algorithmic design space and the performance that this may have. And then the next part is that, when we're going to design a particular data structure and figure out how much it costs, or figure out what is the optimal design given the workload. And so here, what we do, we have a search process where basically we keep querying the base layer of costed access methods, and then every time we are learning how this behaves, how for a given workload, how the performance changes, so we can make the best possible choices. And so we're iterating through different designs, and of course, there's many ways to optimize here behavior. The most exciting thing is what we call the design continuum, where we're actually mix and matching machine learning with analytical models for fast and kind of tractable search in there. What you get in terms of input is that you start with a process that says, given a workload, given a hardware, and some SLA, some restriction, I'm going to go in and search as fast as possible. And then what you get on the other side is really an abstract syntax tree and C++ code for the particular data structure that is the optimal data structure out of all the possible data structures that the system can search through. Now, so that was a quick description of that system that automatically generates data structures. Now, again, the essence of that is that you start from a set of principles. You know how this behave. You know what is when you synthesize them, when you combine them in arbitrary synthesis, what kind of systems you get, what kind of data structures you get. But the next question is, how do we go from that? How do we go from data structures to something more complex, like key value storage engines in this case? And so the first thing that we've done as we started thinking about that is that we said, okay, let's make the problem a little bit simpler by restricting ourselves to a smaller space of data structures that we think it is, very interesting in terms of performance. At least it seems to be very interesting in terms of performance for the industry world. And so we're spanning anything from a B tree to an LSM tree to log plus index. So if you think about this is from highly read optimized, write optimized, and very, very, very write optimized systems. And what we're doing is that we're effectively taking the part of the design space that can describe those families of data structures. We're combining that part of the design space, and we're creating what we call a superstructure, something that describes actually a template that can describe all of them. And so, this can describe anything from actually a log to a sorted array on the other side, which, if you think about this, these are really kind of the extremes on the two ends. And then, of course, the real critical part is, as we discussed in the beginning of the talk, how do we map the interactions between between the different data structures that exist in a key value engine? And so here's how we're really mapping everything from data that may be in memory, that may be on disk, the buffers, the filters, the fence pointers. So really thinking about this step by step and trying to map every single interaction that may have. And at the end of the day, I'm not going to describe the slide in detail, of course, but the way we're doing it is that we created a really detailed model, analytical model, that describes the interactions of those components. And effectively, what you see as red here, marked as red, is components of that analytical model that someone has to give us input. And what you see as gray is components that are actually being automatically derived. And the red part, or the top red part, that is environment, this is actually given. And the only thing that we have to iterate through for automatic design is what you see marked as design. So we actually managed to reduce the problem to five design knobs that we can very easily iterate algorithmically on top of that system. But everything else is derived and optimized automatically. Okay, so I'll stop here at that level of detail, but let me give you a few examples of how this automatic automatically generated Stratos engines that we are creating that can take arbitrary shapes, actually trillions of possible shapes, how they're behaving. So again, what you see here is a few state-of-the-art Stratos engines. So RocksDB in blue is a state-of-the-art LSM3 based system. WireTiger in red is a state-of-the-art B-tree based system. So RocksDB is used by by Facebook, but really by so many. It's a wonderful system by so many different organizations. WireTiger is now used by Mongo, and Faster is a research prototype. It's actually a really wonderful research prototype by Microsoft Research, which is based on logging and an in-memory hash implementation. So Cosine is our own self-designing system that can take multiple different shapes across all those possible families of systems and optimize aggressively for really fine-tuned nodes. And then the idea is that there's a search process based on the workload. You start with a workload and a budget and a cloud budget, and then what you get on the other side is an optimal storage engine in Rust that is just for the particular context. So this is a case where we have a workload that is read heavy, and so what you see is that once you have enough budget, so this is in dollars, we actually Cosine can be an order of magnitude faster than actually faster, and more than an order of magnitude faster than the other systems. And this makes sense in this case because read heavy here is mostly about point queries, where faster is actually great because it's based on hashing. Okay. Then when you have a different kind of workload that is write heavy, now you see that RocksDB, the blue line is actually much better than the red line, WireTiger, and this makes sense because RocksDB is more based on logging, but still faster can improve even more because it has a single level effectively. And there's no range queries in this particular case. And then when we have a mixed kind of workload, again, we see a different kind of behavior in between these other systems. Yet Cosine, our own system, our own self-designing system, because it can take different shapes every time, fundamentally different shapes every time, it optimizes performance substantially across all these workloads. And these are only 3 examples. We've been generating hundreds of different kinds of examples for different kinds of workloads, and the results are consistent. And so the worst case that you may have here is that there is a workload for which there's an existing system is really the best system, and so then Cosine, what we'll do is that we will match exactly that behavior. Okay. With that, I'm coming to an end. And what I want to say is that what I told you about key value storage engines as an application on top of the automatic data structure design research that we're doing is really just a layer. And so we're doing more research into how you can do SQL on top of that substrate of data structures, how you can do machine learning efficiently, how you can do statistics, images, video, and graphs efficiently. And so we're using that for even more complex applications than key value engines, and we're also thinking about how all those things combine together as well. Also, keep an eye for a startup that might be coming in the next few months out of the space, and if people are interested, please reach out. With that, I wanna close by bringing up the faces of our students at Harvard Dash Lab, and really thank you for your attention, and I'm really happy to take any questions you might have. Thanks a lot.
Thanks a lot, Stratos. It's a fascinating work. I think it's going to be great to see it impacting a lot more infrastructure. Since we are a little bit behind time, I have time only for one question. So I'm curious about your thoughts on integrating this kind of technology into, I guess, somewhat more mainstream technologies, like maybe integrating it with PGO for regular compilers or JIT compilers for managed languages.
Yeah, so this is a great question. And let me start by saying also live, thank you for the invitation. Very glad to be here. And I'm going to be online through the day if people have questions on Slack. So I think it's very exciting to think about integrating these kind of outside data systems in compilers or operating systems. This is not something that we have done specifically for compilers or operating systems, but you definitely have the same kind of problems there in that you have data structures being pressured by different kinds of diverse queries, especially I think in operating systems, because people are doing so many different things. So you have really diverse workloads. And so again, you can imagine a system where there's a black box, and that black box has not, nobody has to program it. It's just a black box that all you need to know is that it's going to do put, get, delete, and maybe range queries or some subset of that, and that's the input that you need to give it, and then it takes the shape of that as the system is being used, as opposed to the developer, we having to use the right data structure out of some library or develop our own. So I can totally see a future in that space. Of course, there's problems that if you have a black box, you have to maintain it, you have to make sure it's robust, and these are very, very critical issues. You have to be able to debug it, and if you haven't developed something, how do you debug it? How do you trust it? So definitely there's a lot of actual critical problems there to be careful of, but we actually have those problems today anyways. And so I think there's an interesting future in that direction. Yeah.
Awesome, because we actually had at our previous summit, we had a talk about the Darwinian data structures, which is a little bit similar, I guess, in some regards, where basically they monitor they essentially use profile-guided optimizations to decide what would be the optimal data structure for a particular use case, and then they automatically suggest it. So for example, if you notice that your array is usually pretty small and you usually traverse it linearly, then array list implementation is the best one. But if you have, let's say, some random inserts or whatnot, and for some reason linked list it becomes more efficient, then they just recommend that. So I hope that at some point it's going to be as easy for your work as well, where we will just be benefiting from the most optimal data structures without having to constantly remeasure these things, because obviously what is most efficient today on current hardware may not be as efficient and not as optimal on a different hardware tomorrow, when we all move to M1 chips and everything is ARM and nobody uses Intel. So yeah, well, as I mentioned, unfortunately we're a little bit behind the time, but fortunately we will have you for the panel discussion, so I hope we can continue our discussion there. So thank you so much again, and I'll see you later.